Yes, that's right. Thank you, Hui, for the introduction. Thanks to the organizers for the invitation and for the opportunity to speak here. And thank to you all for coming to this, I think, earliest talk of the conference. I will speak about a series of 4 joint papers together with Xavi. And the last paper is also co-authored with Begoña Barrios from Tenerife. And all of these papers deal with non-local free boundary problems, and in particular with the non-local one-phase problem, so non-local version of the Alt-Caffarelli problem. And my goal for this talk is to first give at least a brief introduction into what these non-local free boundary problems are, or why it's interesting to study non-local operators, like what are the main novelties that you get when you deal with non-local problems, in order to motivate somehow what the main challenges will be and have been for us in our works, and then I will explain what the main results are that we were able to obtain. Okay, so let me start very basic. So this is just a slide to introduce you to the fractional Laplacian. I guess everyone here has seen this many times, but I want to emphasize that throughout this talk, it will be very important for me that the operators that we deal with are not the fractional Laplacian, but they are more general, okay? All the operators will somehow be modeled upon this fractional Laplacian here, but they will be more general in the sense that you will see on the next slide. So just let me make 2 comments on the fractional Laplacian. I guess you all know it. So you take this integral here of the second order increment of your function, and then you have this kernel here, which has a singularity at the origin. So this integral only converges if your function has certain regularity, right? So in this way, it's an integro-differential operator. And what is important here is that this weight is a radial function, okay? And what I will change on the next slides is precisely that this rate will no longer be radial, and this will lead to some complications. And there are also some motivations to study these more general operators. Okay, and the main question that will be present in this talk, but also is present in all the research that has been done on non-local problems, is basically this fundamental question here: in what way does non-locality that you see in this operator influence regularity properties for PDEs? Okay, and non-locality here enters on very small scales, but also on very large scales, in the sense that instead of having derivatives here, even when h is very small, you only have these increments, so no derivatives, but you have increments. And then at the same time, you also have non-locality in a very long-range sense, because when you want to evaluate this operator at x, you need to know the function everywhere in space. So what could happen is that if you solve an equation in some bounded domain, and you have very bad exterior data, they might affect the regularity of the solution inside the solution domain. Okay, and the question is whether this actually leads to new effects or not, and in what way one can tackle these problems. All right, so as I already said, the goal of this talk is not to speak about the fractional Laplacian, but about a more general family of non-local operators, and this family you can see in this box. So what I did was I basically took the fractional Laplacian, but this weight here, this kernel, I multiplied it with the function k that lives on the sphere. Okay, and what it means, what it does, is that you have an operator that can be anisotropic, right? So when you sit at a point x and you look at your increments in a direction h, then the weight that you put can depend on the angle of h. Yeah? So it leads to anisotropy in your model, and this leads to additional difficulties, and also and these difficulties are not just, okay, we put this function, but they are really technical issues, as you will see throughout the rest of the talk, that make these operators much more complicated to study than just the fractional Laplacian. So why is it a natural class of operators to consider? Well, when you think about probability theory, for example, then you might know that the fractional Laplacian generates some jump processes, some Levy jump processes, and this jump process that is generated by the fractional Laplacian is rotationally symmetric. So jumps in any direction can appear with the same probability. Now, when you consider operators like this, then also here jumps in different directions occur with different probabilities. And under this assumption here that you have this function k that lives on the sphere and that is somehow comparable, like that is bounded from above and below, you get a class of generators that corresponds to the class of 2s stable processes. And this is a very well-studied class in probability theory. Then also people have studied more general versions of these operators. For example, you can make these kernels also x-dependent. Then you get operators with coefficients in a sense. And then you can use variational tools or viscosity solution tools to study these operators. And there's a wide range of literature on these kind of operators. Also, a motivation to study these operators that somehow came to my attention very recently, and that's very interesting for me, is that these operators, they somehow appear in linearized models of the Boltzmann equation, which is an equation from kinetic theory. And there you have a velocity variable and a space variable. And in the velocity variable, these operators here, these non-local operators, they appear. So it's a natural quantity also there. We've seen already talks about non-local minimal surfaces. Also there, people have studied these kind of more general operators. And today what I will speak about is non-local free boundary problems, which is another direction where one can consider these operators. So many people have studied this theory, and during the past 20 years, it has become quite an active field of research. All right, so I want to now give you at least 2 or 3 results that are very classical in the theory of non-local PDEs to somehow give you a feeling, for those of you that are not too familiar, in what way non-locality creates problems or new effects. And then we will see that all of these effects or these non-local particularities, they will also occur in the study of free boundary problems. So you can see this somehow as a preparation, this slide and the next one. So the first general fact is that these non-local operators that I would consider, they are regularizing, right? They are of order 2s. So what you can have is you can prove Schauder estimates of this form. Yeah? When you have kernels, these functions on the spheres, when they are Hölder continuous and you have source terms that are Hölder continuous, then you can prove that your solutions are of order 2s plus alpha. So you gain 2s derivatives compared to your data because the operator is of order 2s. That's a very general fact that is very well known. Results of this form have been generalized a lot in the past years. Also, you can ask about Harnack inequalities, right? When you have a non-negative solution, is your supremum comparable to your infimum? And also here, the answer is yes, you can prove something like this, but the non-locality somehow makes your life much harder because it turns out that this Harnack inequality might fail if you assume your solution to be only non-negative in the ball. Yeah? So what might happen is that when you have a solution that is non-negative in the ball, but outside the solution domain it becomes negative, then this non-locality might influence the values of your solution inside and make the supremum and infimum no longer comparable of this form. So what you usually have to do in non-local regularity theory is you have to account for non-locality in a certain sense. And for the Harnack inequality, you need to add an additional quantity that somehow measures how negative the function can be outside. And the way this is measured is in terms of these so-called tail terms here. So you have an integral quantity where the weight that you put is somehow the weight that you had in your non-local operator. So somehow what happens very far away matters less, but you have to include it in your estimates because otherwise they fail. On the other hand, in this interior estimate here, also non-locality enters because although on the left-hand side you just have a local estimate, on the right-hand side you really need to take the infinity norm of your function in the full space. If you just take information in a slightly larger ball, the estimate will fail. So far, so good. So long-range interactions always have to be taken into account. But apart from that, these results are pretty analogous to what we see in the local theory. However, this changes when we don't consider any more interior regularity estimates, but boundary estimates. So this is what the next slide is going to be about. And of course, studying the boundary regularity for a fixed boundary is like the baby step if you want to consider free boundary problems, right? So let's understand what happens at the boundary for those of you that are not too familiar with this. So in the local case, of course, when you have a smooth domain, then your interior regularity matches the boundary regularity, right? If your domain is smooth, solutions are smooth up to the boundary, everything is analogous to the interior case, somehow more technical to study, but the results are similar. Now, in the non-local case, this is completely different. It turns out that already in the simplest case, when your operator is just a fractional Laplacian and your domain is just a unit ball, and you take your right-hand side f to be just a constant function, then you get solutions that are not C infinity. In fact, you get this explicit example of a function that is only CS up to the boundary, but not better, yeah, where 2s was the order of this operator. There are explicit examples that you can compute, and at the boundary, you can in general not be better than CS. All right. And this result stays the same if you make this operator more general. You cannot be better than CS in general. Okay, so that of course makes the study of non-local free boundary problems more challenging because you see that when you take your harmonic function with respect to this operator, there will be no well-defined gradient at the boundary, right? So you will always have exploding gradients, and this makes the study much harder because many tools that are available in the local case, you just don't have them. However, you can prove something slightly better, or actually not slightly, but much better, if you don't look for regularity of the solution itself, but for some sort of non-local gradient of your solution. So it turns out that when you look at the same problem as on the previous slide, so you solve the Dirichlet problem somehow, I wrote it here in a localized setting, then, of course, if your domain is like C1 alpha, your right-hand side is L infinity, then solutions will only be CS. That's what I told you already before. But it turns out that when your domain is nice enough and your kernel and your right-hand side are also nice enough, then when you take the solution U and you divide it at a point X by its distance to the boundary and take this distance to the boundary to the power S, then this quotient as a function of X can be much more regular. It can be CK minus 1 alpha. So in a sense, you can think of this quotient as some sort of non-local normal derivative, because when S is equal to 1 and you take this limit to the boundary point, then you get the actual normal derivative, and then you can prove regularity for this, that is of higher order. So you can develop also a sort of Schauder theory up to the boundary for these non-local operators. And now, one natural way to motivate or to introduce free boundary problems, or the one-phase problem in particular, would be the question whether, when you see such a result, whether you can also reverse the errors here, right? Whether, I mean, here this result says if the domain is nice, then the solution is nice, or this normal derivative is nice. Can you also reverse the errors in the sense that if you have a solution that satisfies this property, if your domain admits a solution that satisfies this property, that this normal derivative is nice, does this mean that also the domain must be nice? And this is a natural question that leads to the Altka-Farelli problem. And one goal of this talk will be to answer this question, namely exactly what I said before. If this quotient is nice, does this mean that the domain is nice? If you think about the local case, then when you take U to be the green function, then the normal derivative of the green function would be the Poisson kernel, right? So somehow we have here a character, like a relation, a non-local version of the harmonic measure, and we relate it to boundary properties, regularity of the boundary of certain domains. Okay, so this will be one goal of the talk, to answer this question towards the very end. All right, so now let me tell you what non-local free boundary problems are, and I will just speak about the two prototype problems, the obstacle problem and the one-phase problem, and then I will explain what results we can get on this one-phase or Altka-Farelli type problem. All right, so the setting is not really different from everything that I told you before. You take this function k that lives on the sphere. It should be bounded away from 0 and from infinity, and then you consider this energy, this double integral here. And when you just minimize now this non-local energy in a suitable function space like HS, let's say, then minimizers of this functional, if you put suitable boundary conditions, of course, they will solve an equation that is LU equals 0, where the operator L was the operator that I introduced at the very beginning. This is non-local operator modeled upon the fractional Laplacian. Now you get free boundary problems, of course, in analogy to the local case, if you put a constraint to this minimization. If you add some further terms. So the obstacle problem, you would get it if you minimize this non-local energy over all functions in HS that lie above a certain obstacle. It's a very natural way, in complete analogy to the local case, how you could define a non-local obstacle problem. And this has been studied already, well, almost 20 years ago in the case that k is equal to 1, in which case you just get the fractional Laplacian. And there, optimum regularity of solutions has been understood, and also the free boundary. There are many results, in particular on the free boundary near regular points, is quite well understood. And the earliest works are here from Silvestre and Caffarelli, Salsa, Silvestre. However, when you take a more general kernel here, when k is not just equal to 1, then it has remained an open problem for quite a while whether you can obtain similar results like optimal regularity of solutions, and also whether you can classify blowups near regular points. And there's this recent, or not so recent anymore, paper by Caffarelli, Ros-Oton, and Serra where this has been done. For the one-phase problem, however, the situation looks a bit different in the sense that also here, for the fractional Laplacian case, there are many results, but nothing has been known for general kernels. And that's precisely the goal of this talk, to somehow fill this gap and to explain what happens in the one-phase problem when you put a general kernel. So what is the one-phase problem? Well, it's also in analogy to the local case. You minimize this non-local energy, and then you add here the measure of the positivity set of your minimizer. Okay? So somehow it forces it penalizes your minimizer to be positive. So you go to, you want to go to 0. In the positivity set, you will solve a non-local equation that that corresponds to this non-local energy. That's what you want. That's what you will get. And as I said before, in the case that k is equal to 1, when this is just the fractional Laplacian, the HS semi-norm, then many results are known. For example, the optimal regularity of the solutions is known. Also, like flatness implies C1 alpha theory has been known. Also, higher regularity of the free boundary near regular points. There are many papers that I listed, by far not all of them in this area. But nothing is known when k is not equal to 1. Okay, so why is that? Why is the case k equal to 1 special, and why is it more difficult or more challenging or also interesting to study these general kernels? Well, there are several reasons. The main reason is somehow that when you have the fractional Laplacian, so when k is equal to 1, you have a lot more tools available that completely fall apart when k is not equal to 1. The main argument would be that you have this Caffarelli-Silvestre extension when k is equal to 1, which allows you to identify this non-local problem with an equivalent local problem where your free boundary will only occur in a thin space. Yeah? So there's the thin obstacle problem, there's also the thin one-phase problem, and you get them precisely when you take k equal to 1 and s equal to 1/2. Yeah? So there's a relation between these non-local problems and these thin free boundary problems. And when you have this thin problem, then somehow the non-locality is hidden, right? So that you hide the non-locality, you hide these long-range interactions that I was advertising on my first slides. But the price you pay is that somehow the geometry of your problem becomes more complicated. But still, you have gradients, you have derivatives, you can construct barrier functions much easier than if you deal with this non-local quantity. Also, a key point is that once you have this Caffarelli-Silvestre extension and you have this thin problem, you will be able to prove monotonicity formulas. Yeah? And monotonicity formulas, as we all know, they are crucial in the study of the classification of blowups because they give you homogeneity. In these more general problems where you have anisotropy, you cannot expect any monotonicity formula. Yeah? So you really need to bypass monotonicity formulas in everything that you do. All right, so as I said, the goal of this talk will be to explain what we can do for this non-local one-phase problem. And although this is a free boundary conference, I want to spend now maybe a few minutes, not too much, but only a few minutes, giving you a brief, let's say, recap of what are the typical results for the one-phase problem. But luckily, I can be rather fast because we had 2 talks yesterday where this was also already repeated. I just want to do it for the sake of completeness, and then we can compare later in a better way in what way the non-local world is different from the local world. Okay, so in the local case, the one-phase problem, we've seen it now many times. So instead of taking the HS semi-norm, you take the H1 semi-norm, and you put this measure of the positivity set. And then we've also seen the Euler-Lagrange equation already yesterday. So you will be a harmonic function in the positivity set. Then you have your region where you're 0. And then on the free boundary, you have a free boundary condition. And this free boundary condition is basically telling you that the normal derivative is constant. The normal derivative of your solution there is constant. And then you can ask, what is the optimal regularity of solutions? What can you say about the free boundary? And the answer is that the regularity of solutions is in general only Lipschitz. You cannot be better than Lipschitz in general. And then for the regularity of the free boundary, many results are known. And the most, let's say the most famous one, or the pioneering one, due to Alt and Caffarelli, it establishes that near flat free boundary points, the free boundary is C1 alpha. And then you can bootstrap and prove that near flat free boundary points, you're actually a C infinity, you're actually an analytic free boundary. And the main idea to prove such a result, we will see, I repeat it here because we will see a similar kind of scheme also in the non-local case, is a classification of blowups and an improvement of flatness, right? So the intuition is, as usual, you fix a free boundary point. And when the picture looks like this, that when you consider your blow-up sequence and in the limit you get something one-dimensional, like here, then you expect the free boundary to be C1 alpha, and then you expect it also to be smooth later by bootstrap argument. So, and then your flat free boundary points, the free boundary is also C1 alpha because you can prove that when the free bound when you have this picture, the free boundary must in particular be flat, right? So what means flat? Flat means that you can trap your free boundary near such a point between 2 parallel hypersurfaces that are close to each other, right? So near these points, whenever you have these free boundary points where the free boundary can be trapped in between two parallel hypersurfaces that are very close to each other, you will see this picture and you can prove that the free boundary will be C1 alpha near these points. So the key is, of course, to classify these blowups, to understand when is the free boundary flat, when do you get this picture. And as we've seen already yesterday, there are several results in this direction, but also several results are still open. So it's well known that this classification of blowups always gives you this one-dimensional situation in 2D, right? And in 3 and 4D, it was proved much later by Caffarelli, Jerison, Koenig, and Jerison, Savin. And in dimensions 5 and 6, this is still open, right? So in dimensions 5 and 6, it's not known whether all blowups will look like this or whether there are counterexamples. However, in dimension 7 is the first where you see counterexamples. Then in higher dimensions, you can still prove like Hausdorff dimension bounds for the singular set by some dimension reduction arguments. And also you can study, that was something that Xavi was like briefly announcing to us yesterday, you can study generic regularity of these one-phase problems too, of course. So you can study how big is the singular set generically. Okay, and of course, the key to all of these classification results is, let me emphasize this once more, that you have monotonicity formulas, right? You know that all your blowups will be one homogeneous, and this simplifies the classification procedure a lot. And in this non-local framework that I will be considering, we don't have them. Yeah? So we need to do something else, or we need to try to get as far as we can without using these monotonicity formulas. All right, so what is the non-local one-phase problem? I've told you already, you want to minimize this non-local energy. Instead of having here the H1 seminorm, we take this non-local double integral and we have this kernel K that is a function supported on the sphere. And now the Euler-Lagrange equation is something that you can guess easily by now, I think. So in the positivity set, you will not be harmonic with respect to the Laplacian, but with respect to this non-local operator L that I wrote here, yeah, which I started my talk with. And then you will also have a condition on the free boundary whenever the free boundary is nice enough. And this condition will not be that the normal vector satisfies a certain property, because in general you cannot expect the solution to have bounded derivatives up to the boundary. But this non-local normal derivative that I defined before, that appeared before in these boundary regularity results, this is something whose value you can prescribe on the boundary. And now what happens, and this is also an additional difficulty that you only see when k is not equal to 1, it turns out that this non-local normal derivative is not constant on the boundary. Okay, it's not constant. It's this function here, a of nu, where nu is the normal vector on the free boundary, and this function a, it depends somehow on the kernel. It's in some sense related to the Fourier symbol of this non-local operator, for those of you that are familiar with this. And in particular, because you have a non-constant normal derivative here, it makes your study much harder because, well, you don't know a priori where the free boundary is, right? So it also means you don't know the normal vector, and therefore it's very implicit somehow what is this condition, right? It creates many additional problems. But what you can prove, and this is not so difficult to see, is actually this one-dimensional blow-up. Yeah, you can easily come up with a guess what this one-dimensional blow-up is, and it's this solution. Yeah, so in the flat case, when your zero set is the half space, you don't grow linearly, but you grow like x to the s. Yeah, this will be the solution in the half space to this Euler-Lagrange equation. Okay, so this is what we will see. But also here you see that this blow-up, it does not have bounded derivatives at the free boundary, right? So also this we will see later creates problems. All right, so what can we prove? The first result is, of course, what is the optimal regularity in this problem? In the local case, we saw that minimizers are in general Lipschitz and not better. Here we can prove that they are CS, and also that this is optimal because we just saw this one-dimensional function that was only CS and not better. Yeah, so what this result is an upper bound and also a lower bound, so we have like precise control about how the function grows at a free boundary point, right? So when you have a free boundary point, your function is somehow trapped in between two multiples of x plus to the s. Right? Your solution is somehow trapped in between here. So you have a non-degeneracy, and you also have the regularity from this upper bound. And what you can observe when you look at this when you look at this estimate is that we have a non-local equation here, but still this estimate is a local estimate in the sense that this constant here, it does not depend on anything else, and it does not depend on the solution at all. It does not depend on its tail or anything. It only depends on the dimension and maybe on the ellipticity constants of this k and maybe on s, right? So it's an entirely local estimate, although this is a non-local problem. And the way that we can make this estimate local is by using a certain purely non-local result that I put here on this slide. So it turns out that in non-local problems, sometimes you can control non-local terms, like these tail terms, by local quantities if you solve certain problems. Yeah, so in a sense, when you look at this quantity, you've seen it already in this Harnack inequality. There was this non-local term that was measuring somehow how negative you are. Here in this one-phase problem, you have a similar quantity. So this measures somehow, when you are in a ball, it measures the values of your solution or of your minimizer outside the ball. So in particular, the values at infinity. And it puts this weight. And this quantity, you can bound it by local quantities only. You can somehow bound the exterior by the interior. Yeah? This is somehow like a reverse maximum principle, if you like. Something that you only have for non-local problems. And this estimate that we prove for this one-phase problem, it allows you to localize this estimate completely. Okay, so once we have the CS regularity and the non-degeneracy, then of course we are open, the road is open to study blowups, because we can now do these rescalings and we have enough compactness to pass the blowup sequences to the limit. So the question that now follows is, of course, can we prove that whenever the blowup is one-dimensional, that the free boundary is nice? And also, what can we say about the classification of blowups? Okay, and this is somewhat the main result, or the first main result of this talk. So what you see here is a complete analog of the flatness. Yes? Yes, yes. What do you mean, both? From above and from below you? Yes, we can control both. Yes. Yeah, so what you see on this slide is, in a sense, is a complete analog of the flatness implies C1 alpha results of Alt and Caffarelli that we also establish in this non-local framework. Okay? And this result, but also all of the other results that I already presented and will present in the rest of the talk, they were only known for the fractional Laplacian, and nothing was known for these more general operators. And in particular, let me emphasize this once more, all the results for the fractional Laplacian that were already obtained, they were obtained using this Caffarelli-Silvestre extension, using this thin problem and local features very heavily. And we wanted to develop a non-local approach that really does not hide the non-locality, but uses it, like to understand what the non-local effects really give you. And here we have a non-local analog of this flatness implies C1 alpha result. So the result is very analogous to the local case. So when the free boundary is flat near a point, then we can show that it must actually be C1 alpha in a small ball. Okay, and then by this boundary regularity results that I was mentioning at the beginning, you also get these kind of regularity estimates for your solutions up to the bound. And then in particular, we actually prove that when your blowup looks like this, then the free boundary is C1 alpha, so that's how you can get it near flat points. Okay, so I will explain later, like at least some ideas from the proof. I will, of course, not go into too much detail, but later I want to at least like give you a few like glimpses of arguments that enter, because there are some aspects that are very different from the local case, and also some problems appear, some non-local problems appear that are quite interesting and have not been studied too much in the past. So I will make some statements about the proof later. For now, I want to continue on the question, now that we have this flatness implies C1 alpha result, what can we actually say about classification of blowups, right? Because now you're asking, of course, how big is this set of regular points? And it turns out that in 2 dimensions, we can classify all the blowups, right? So as I said before, we don't have any monotonicity formulas, which makes the classification of blowups in general very hard. But at least in 2 dimensions, we can bypass monotonicity formulas and prove that every blowup is actually this one-dimensional one, and therefore the free boundary is C1 alpha in 2 dimensions always, okay, for all of these kernels that we consider. And the main idea to do this, I also here don't want to go into too much detail, but we're using a certain competitor argument well, we got the inspiration from this paper by Savin and by Enrico, where they use like similar competitor arguments in the theory of minimal surfaces, of non-local minimal surfaces, and we adapted this technique somehow to the non-local one-phase problem. So what you get is when you do the competitor argument, the idea of the competitor argument is somehow you fix a number t and you fix a vector e, and then you somehow translate your solution locally in the e direction, and then you can produce these kind of incremental quotients. Okay? And when you run the competitor argument, you can produce these incremental quotients, these L1 norms of incremental quotients, and you can bound them by a quantity like this. And this holds true whenever you have a minimizer in a ball with radius r. Okay? And now it turns out that when the dimension n is equal to 2, and you set r to infinity, then this right-hand side actually goes to 0. And what it tells you is that because this product is 0, that one of the two quantities must be 0. And this is enough to conclude that this minimizer, this global minimizer, will be monotone in every direction, right? Because one of these two functions, one of these two factors must be 0 always. And when you're monotone in every direction, then it means that you're a one-dimensional function. And when you're a one-dimensional function that solves the one-phase problem, then you have a Liouville theorem, and you can show that then necessarily you must be this one-dimensional blob. Yeah, so I will explain a little bit more about this, like how to get this in a second. I just wanted to put the estimate first. So it's something that only works in 2 dimensions, because in higher dimensions, this quantity will not go to 0. But it bypasses monotonicity formulas and allows us to classify blowups in 2D. This is something that was also only known for the fractional Laplacian before, using monotonicity formulas. So this argument is new. And in higher dimensions, it's completely open what happens, and also for the fractional Laplacian, it's completely open what happens. There are some classification of blow-up results for actually symmetric solutions, but not in a general framework. So I just want to make 1 or 2 comments on how you can prove something like this, because it's a purely non-local argument. Yeah? So this is an argument that only works if you have non-local energies, and it does not work in a local case. And here you're somehow using to your advantage something that is usually a problem when you deal with non-local equations, because what you don't have in non-local problems is, because you don't have derivatives, you don't have a product rule or a chain rule. And this usually creates problems when you want to prove regularity. But sometimes what you do is you replace these non-local, like you try to prove some sort of non-local chain or product rules by using algebraic estimates, so algebraic inequalities for numbers, by estimating differences and sums. And sometimes when you do this, this leads to quantities that you don't see in the local case that have a sign that actually helps you. And this is something that you see here. So when you look at this for a second, if you take 2 functions, w and phi, and then you take their minimum, and then you take its gradient and square it, and you do the same with their maximum, then it's very easy to see that what you will get is just the sum of the gradient squared of the 2 functions, right? When you want to prove something like this in the non-local case, you will replace the gradient by a difference like this. Do this with the minimum, you do this with the maximum. So this term corresponds to this one, this to this one, and then you also get the gradient of w squared and the gradient of phi squared. But you get an error term that I wrote here in red, and this error term has a sign. And when you put it on the other side, then it's exactly what you see here. If you call u of x, w of x, and phi of x, this shift, this competitor. So using such an algebraic equality and doing this competitor argument that I was telling before, where the competitor somehow produces these shifts of u in a certain direction, you can gain information from this term which has a sign. And then you can classify blowups at least in 2 dimensions. Okay, so in higher dimensions, as I said before, classification of blowups is open. We don't know how to do this because we don't have any monotonicity formula. There's somehow there are too few tools to start this. But what we can prove at least is that the set of regular points is open and dense. Yeah? We prove this because by the observation that whenever you have a free boundary point that can be touched by such a ball here, then you can show that the blowup at this point also must be the one-dimensional one. Yeah? And for any set, the set that can be touched by balls like this is open and dense. Yeah? This is how we prove it. Okay, so now I want to make a few comments about how we prove this improvement of flatness. The slide looks technical, but I will not go into too much detail. I want to focus on the ideas and on the difficulties that you get when you have a non-local problem like this one. Okay, so I guess it's not going to be too technical. So let me just remind you, so we want to show that whenever you have this picture here, so whenever your blow-up limit is one-dimensional, that the free boundary is C1 alpha at this point. Okay, and the idea to prove this is we adapt somehow this improvement of flatness epsilon regularity theory, the proof by Daniela de Silva. Okay, so what it means is we start by assuming that when you rescale your solution, when you rescale your solution, you can actually trap it in between two translations of your one-dimensional blow-up. Yeah? So for every epsilon, for every error epsilon, there exists an R, so that when you zoom in up to scale R, you can trap your solution in between these translations of your one-dimensional blow-up. That's something that you can always guarantee whenever you're in this picture, right? That's what flatness means. And then the idea of the improvement of flatness is, well, you zoom in a little bit more, and then in a quantitative way, you can make this error smaller, right? And when you do this in a quantitative way, you can iterate it, and then you gain C1 alpha regularity of the free boundary. Now, in the non-local case, we want to do the same. However, it turns out that when you use this information, there's no way to get here. And the reason is that this is a very local property. You only claim that this holds true in a ball, but you have a non-local problem, so you need to somehow take into account what happens outside. And it turns out that the best way, at least for us, to do this was we also need to impose that we are somewhat close to this one-dimensional blow-up outside the ball. Yeah? And the right way for us to measure this closeness outside the ball is by taking, again, these sort of non-local tail terms, these weighted integrals, where we measure the error here, but we put this weight that decays like the kernel of the fraction Laplacian, and then we integrate, and we also need this integral quantity to be small. Okay? And also this is something you can always guarantee by just zooming in a bit further, and then you also get this smallness. And then what we have to show is that when you zoom in more, not only this error here decreases, but also this red error decreases. Okay, so what we need to do is on every scale, we have to track exactly what is the error like locally and what is it non-locally, and we have to track it on every scale to improve it locally and also non-locally. Okay, so this leads to quite technical arguments, but in the end you can do it, and then you can just use this information to get the C1 alpha regularity of the free boundary. Okay, so you need to take into account long-range interactions, but there's also another thing that I want to highlight, and this is what the linearized problem is. Okay, so as most of you, I guess, know, the main idea to prove 2 is that you prove it by contradiction, right? So you assume that that there's a sequence of errors epsilon k for which your sequence uk satisfies this flatness condition, and then you assume that this fails, and then you can get a contradiction. And the way that you get the contradiction is you can show that when you have the sequence of functions uk with an error epsilon k, that you have enough compactness to pass the equation that these uk satisfy to the limit, and then you get the contradiction from the regularity of the limiting problem, the so-called linearized problem. And it turns out that in the local case, the linearized problem is just a Neumann problem, right? You solve Laplace u equals 0, and you have Neumann derivative equals 0. In the non-local case, you also get a certain Neumann problem, but it's very different from the Neumann problem that you would usually consider in non-local theory. And it surprised us a bit that we got it. But then it also led to some interesting, well, actually to hard work, because we had to analyze this problem in a separate paper. But I find this problem that we get in the limit quite interesting, so I wanted to talk about it also now for a few minutes. So what is it that you do? You consider these quotients here, similar to what you would do in the local case. You subtract your your blow-up limit, and then you divide by epsilon, and you want to know what happens in the limit. Well, in the local case, what you would do is you can observe that this flatness condition, actually, you don't need to put these positive parts here, right? When s is equal to 1, you can just extend your function linearly, and then you have a bound of your UK from both sides by harmonic functions. So when you put here not the positive part, but just xn in the local case, it's very easy to see what will be the limiting equation, because when you just apply the Laplacian here, you have that you know what is the Laplacian of UK in the positivity set, because you solve the one-phase problem, and the Laplacian of a harmonic function is just 0, right? Of a linear function is just 0. So for free, you already get then that in the positivity set of UK, you are harmonic, and then because the UKs converge to the one-dimensional blow-up, you know in the end that you will solve Laplace U equals 0. Now, in the non-local case, it's not that easy. You cannot just extend your function. You cannot just get rid of this negative part, of this positive part, because you don't have bounded gradients at the free bound, right? So what we use is an idea that also appeared in the study of the thin one-phase problem. It's called domain variations. But it turns out that in the non-local case, it's much harder to use it, because we cannot construct explicit solutions we cannot construct explicit barrier functions in this case. But let me tell you what is the idea. So the idea is somehow to recast this as a difference quotient, as an incremental quotient of your solution. So you define Vk of x in such a way that this weird quantity is equal to this one-dimensional blow-up. Yeah, so somehow you try to localize the free boundary. And then when you do this, then when you multiply and divide by Vk, then you see that this function that you want to analyze is actually nothing but Vk of x times an incremental quotient of your function uk in the en direction. Yeah? And you can show that these domain variations Vk, they converge. We have enough compactness to show that they converge to some function v. And then this incremental quotient, we can show that it converges to a derivative of your function u in the n direction. Yeah? But then u, because u is the limit of these uk's, u converges to the one-dimensional blow-up, so the derivative is the derivative of the one-dimensional blow-up. So you see this power s minus 1 here. So what you will get in the limit is an equation for this limit of the domain variations v, and this equation is somehow a non-local equation, but it has a weight here that explodes at the hyperplane xn equal to 0. Yeah? So you have a weighted non-local equation with a weight that explodes, and you also get some sort of Neumann derivative here, so it's an oblique derivative. That's why I didn't call it n, because we had this boundary condition that was not constant. You get an oblique derivative here, but it is a non-local equation here with a Neumann derivative that is only imposed on the boundary. Yeah, and this is something that in non-local problems is very atypical in a sense. Usually you solve an equation in a domain and then you impose exterior boundary data. Now here we have a weight that explodes at the boundary, and that means that it's enough to impose boundary condition only on the boundary. Yeah, and of course in the exterior you assume that you are 0 because this function here is 0. Okay, so here you see another picture. So what we have to analyze is the linearized problem, which is this one. We need to prove regularity for this linearized problem. And let me repeat once more, you can look at this picture. If you call this product xn to the s minus 1 times v, if you call it u, then here you have an equation au equal to f in the xn positive part, and here you have u equal to 0, but your function u will naturally explode when it approaches the boundary, right? It will explode at this rate xn to the s minus 1, and then we impose somehow that the normal derivative of this explosion rate is equal to a function g. That's the problem that we consider. And then what we have to show is that this function v that solves these problems actually is a smooth function. Yeah? We need to develop a regularity theory for this linearized problem. And when we realized this, we were a bit upset because this is a problem that has not really been studied before. So somehow in the non-local community, there's this notion of large solutions, and somehow these large solutions, they model exactly what's going on here, but usually they have been analyzed with a Dirichlet boundary condition. And here we have a Neumann boundary condition, so we had to develop a whole regularity theory for these problems. And we did this in a separate paper, and in the end, the outcome is we can prove regularity for these kind of equations too. Yeah? So here I put the simple most result. In the half space, you can show that these functions v I put now that they're only C1 gamma because that's what we need, but actually we can develop a whole Schauder theory of level CK gamma in bounded domains and also with the right dependence on the regularity of F and G. Yeah, so you can show that these functions V solving these equations are actually smooth functions. All right, and then, of course, once you have this, you can do the improvement of flatness strategy with everything that I've just said, and you get the contradiction, and then you can show that the free boundary is actually C1 alpha. Okay, so as the last part of my talk, I want to connect to this statement that I mentioned at the very beginning to motivate the non-local one-phase problem. So a natural question is now, of course, once you know that near regular points the free boundary is C1 alpha, can you actually improve the regularity of the free boundary? Is the free boundary C infinity? And it turns out that, well, the classical tool would be to use a hodograph transform, right? And in non-local problems, it's not so, well, so far no one has managed to do that. And the problem is that you have a non-local equation, but you have a local change of variables. Yeah? So you need to somehow prescribe what is the right exterior datum after you applied your transform. It's not so clear how to make that work. So we need to come up with completely different tools or ideas to do that. In the thin case, so whenever you have the fraction Laplacian, you can apply other kinds of techniques, and it's much easier to prove. Actually, for the case S equal to 1/2, there was this paper already in 2015 by Daniela de Silva and Ovidio Savin, where they proved the higher regularity of the free boundary. And then very recently, like a few weeks ago, there was this paper by Liu, where this result by Daniela de Silva and Ovidio Savin was generalized to general S. What we prove is a result that holds true for all kernels, so we don't need to put just the fraction Laplacian, we just put the general kernel K. However, we are only able to prove at this point that when the free boundary is C2 alpha, then it's C infinity. Okay, so in the one-phase problem, there's this additional difficulty to go from C1 alpha to C2 alpha. We believe it should be possible to either refine this technique or to refine the improvement of flatness a bit more to prove that near flat points you actually see 2 alpha to connect these two worlds. But in the end, we didn't pursue it anymore because with this approach, it seemed like it would make the paper even longer, and it was already very long. So what is the idea that we're using here? I will tell you in a second. But first, I also want to mention this second result here that I was already announcing at the very beginning of my talk. So we can prove that near regular points when there's C2 alpha, the free boundary is C infinity, but we can also prove a finer result that applies to the non-local Dirichlet problem in a sense. Yeah, so I was mentioning at some point in my talk that when the boundary of a fixed domain is smooth, then you can show that U over distance to the S is also smooth. And I was asking, does the reverse direction also hold? And here we have a result that says that indeed the reverse direction also holds. Yeah, so when you look at this overdetermined problem here, you solve your equation LU equals 0 in the ball intersected with a domain. In the exterior, you are 0. And then on the boundary, you impose that this non-local normal derivative is equal to a function h. Then you can show that when your function h is ck alpha, then the domain is actually better. And we can show that it's ck alpha plus 1, and we lose an epsilon with our technique. But if you ignore this loss of an epsilon, then it's really exactly the going into the opposite way. Okay, and also here we need k to be greater or equal to 2 because of the same reason as here. Okay, so what is the idea of the proof? I want to just mention like a few keywords and then I will finish. So the idea that we're using, as I said before, is we cannot use the hodograph transform. So what we're doing is we are investigating similar to what De Silva and Savin did actually in the thin case, but we do it in a completely non-local framework. We are using the observation that because the domain omega that we're dealing with is the positivity set of our solution, that we can characterize the normal vector as the quotient of two partial derivatives. Okay? And then the idea is if we can show, if we start with the ck alpha domain, if we can show that the normal vector is also ck alpha, then it would imply that the domain is actually better, and then one could bootstrap. Yeah, so somehow what we're trying to prove is that we're trying to show that the normal vector is ck alpha by showing that the quotient of two partial derivatives is also ck alpha. Of course, in general, this is not true, right? But what we can expect, or what makes it work for us, is that this quotient of two partial derivatives, because we are not just harmonic functions, but we solve a free boundary problem, they actually solve an equation that allows us to prove this regularity. Okay? So what we're doing is we're trying to derive the equation that holds true for this quotient of two partial derivatives, and then we're developing a regularity theory for this equation. And it turns out that the equation that you get is again some sort of non-local equation with a local boundary condition, with a local Neumann boundary condition. So as I said before, the goal is we want to show that the quotient of two partial derivatives is ck alpha. We want to look at what is the equation that is satisfied by this quotient. So this was the Euler-Lagrange equation that is satisfied by u. You can differentiate this equation, then you get something like this. So you can differentiate the equation like here, and then the boundary condition, you will get something like this. And then you can prove that when you take to the quotient of two partial derivatives, you will still have a certain non-local equation, but it looks like this. Yeah, it's a bit similar to what you see in the local case. Also there, you will get a second order operator in divergence form where the coefficient somehow depends on the derivative of your function u. Similar thing you get here. You get a non-local operator of a similar shape as before, but the kernel is not just this one, but you also have this weight, which is the derivative of your solution u in the n direction. Yeah, but now there's a key difference between the local and the non-local case again, because in the local case, this derivative will be bounded, right? You remember we had the Lipschitz regularity and the non-degeneracy. In the non-local case, you only have CS regularity in general, so these derivatives will not be bounded, but they will explode at the boundary like the distance to the s minus 1. So again here, we have weights, but these weights don't behave nicely, but they actually explode. And then, yeah. I think there's this S multiplying. It's not exactly the same, right? There's this S multiplying. You basically take, what you see is you have u, morally speaking, you have u equal to this function times distance to the s. So when you take a derivative, you will get distance to the s minus 1 from differentiating the distance to the s. That's why you see distance to the s minus 1, and you also see the s. And this is, so this is the same, but the thing that satisfies the boundary condition is different. Yes, that was the... Yes. And the key difficulty here was actually to come up with the right boundary condition. It turned out that that was not so easy because in order to find the right boundary condition here, you need to prove delicate integration by parts formulas for these non-local equations. Okay, and that's something that we had to do in our paper too. And then in the end, it turns out that you satisfy a sort of oblique Neumann condition also on the boundary in this case. Yeah, when you have the fraction Laplacian, then this is really a Neumann boundary condition. But the key difficulty was somehow that when you have an operator here where your kernel is not just 1, but you have a function on the sphere, then it's not so easy to guess what is the right direction in which your derivative is actually 0. And we find that we find this vector theta is somehow parallel to the gradient of this function A. I will not tell you how exactly, but it's basically, you can guess it once you have these integration by parts formulas for these non-local equations. Okay, and then what we do is we develop a regularity theory in our paper together with Begonia and Xavi. We develop a regularity theory for this different class of non-local equations with ways that also satisfy a non-local boundary condition. And by using this regularity theory, we can then in the end indeed prove that this quotient of two partial derivatives is ck alpha, and then we can do this bootstrap argument that I was mentioning on my previous slide. Okay, so this somehow wraps up the theory for the non-local one-phase problem. So what we established, just to summarize, is somehow a complete analog of the theory that is known in the local case and also for the fraction Laplacian. But all the arguments that I presented to you here, they were entirely non-local in the sense that we did not use any extension, but really used the non-locality, and this led to new equations that we had to analyze and also to additional difficulties, as you saw in the talk. So thank you very much.